Yeah, sir, we are ready. Whenever you feel, you can start.
Visible? Right.
Yeah, it's visible. Yeah.
Okay, fine. Do you think I should enlarge it, or is it good enough?
Yeah, if possible.
Is it okay?
Yeah, now it's, yeah.
Okay.
Perfect.
Okay, enlarge it a bit.
So can you make it full screen? Is it possible?
Yeah, you can make it, but okay. The full screen sometimes hides those controls.
Ah, okay. Yeah.
No, it's okay. Yeah, I think this is good enough.
Yeah.
So I think it's time to probably start.
Yes, sir, please.
Okay. So let me welcome you all to this session of Math Clinic. In case this is your first occurrence in Math Clinic talks, I am I'm Dr. Rana, Inder Rana. And we started this initiative, Math Clinic, to help the students understand various topics, overviews, insights, and so on. So today's talk is on integration, historical development of integration, the concept of integration. Basically, I have titled it as Integration from Antiquity to Riemann, and time permitting will go beyond also. Integration is normally taught after differentiation in our curricula. I think for science students, calculus enters into picture 10th standard or 11th standard. And the first thing that we introduce to them is the concept of limit, differentiation, and then later on, once the fundamental theorem of calculus is proved, integration starts as a bag full of formulas and computations. But historically, integration developed before differential calculus. So let me begin formally with my presentation. So the aim of this presentation is to trace, as I said, the development of the concept of integration from the Greek period, that is around 400 BC before Christ, to the modern times. In what way, what is the definition of integration I'm taking to trace out this historical development is, we perceive integration as a mathematical tool related to the physical measurement of length, areas, and volumes. So with that in mind, the historical concepts are developed. Okay, this talk is basically with this definition of integration. So I have divided this into 4 parts. The first part is the antiquity, that is from around 400 BC to 200 BC, that is integration in antiquity. And then there is there was a lull in the development of integration. So there is a jump from 200 BC to around 1700 AD. That is the beginning of 18th century. So we'll say something about that. And then I have singled out contribution of Cauchy in that. So that is the period 1789 to 87. That is a period of Cauchy. What was his contributions? And then move over to contributions of Riemann, which is a period from 1822 to 1866. And beyond that, till possibly today, whatever it is, time remains, we'll try to spend some time on that. So let me begin with the first part of the journey, namely integration in antiquity. I have signaled out the names of the contributors. Antiphon. Some of you, if you don't know what is antiquity, that is a Greek period. Okay. Antiphon. This is, I think there is 0 missing here. This is 480. Okay, to 411. Eudoxus, that is 408 to around 355 BC. And Euclid, not, I think exact era is not known. So it is around approximately 300 years before Christ. And then Archimedes from 287 to 212. So these are the 4 main contributors which I have selected to say something about them. First of all, let's look at what Antiphon did. He was the first to introduce, there is something called method of exhaustion, which was the main tool for computation of areas, volumes by the Greek mathematicians. I will say something about it a bit later. He used this method to find simple polygons to approximate the areas enclosed by for more complicated curves, areas enclosed by more complicated curves. But he did not formulate this method very rigorously. This was only a heuristic way of saying what this method is and how it can be used. Next comes Eudoxus. He was 408 to 355. He was the first one to introduce some kind of formalism in what we do it nowadays in mathematics, like writing propositions and lemmas and so on. So he was the first one to introduce that way of writing mathematics. by considering numbers as ratios of lengths. Okay, numbers were not defined as numbers at that Greek times. They were only ratios of lengths. He paved the way for what is called the rational numbers. So he was the one who defined arithmetic of rational numbers. And he improved upon the method of exhaustion given by Antiphon. So he perfected more or less in his own way. Okay, so I'm sorry, I missed something. And that is Euclid, the important considerations. He used the method of exhaustion extensively to various other geometrical shapes such as cones, pyramids, cylinders, and spheres, finding areas and volumes of such things. His work is compiled in his what we call as the books of the elements. Okay, so that is a bit of history, their contributions. Next comes Archimedes, one of the main contributors of that era. He made the method of exhaustion more general. Okay, he almost sort of perfected it. He found formulas for the surface areas and volumes of solids such as sphere, from rectilinear to going to more figures, cones and paraboloids. His method of integration was remarkably modern, considering that he did not have algebra, he did not have the concept of function, and even the decimal representation of numbers. All such things were not available to him, but still he could do integration, computation of these things very clearly. And origin of notion of tangent is also attributed to the method of Archimedes. For example, what we call as Archimedean spiral, what could be defined as the tangent to Archimedean spiral was given by Archimedes. Okay, so let us come to what is this principle of exhaustion I have been talking about. Let me write, as I found in the books on math history, the given two unequal magnitudes, you are given two magnitude you should think of as numbers in the modern times, but they did not have the concept of a number, so they treated only in terms of magnitudes. So given two unequal magnitudes, from the greater of which is subtracted a magnitude larger than its half. So you're given two magnitudes, and from one remove something more than one half of the other smaller one. And from the what is left out, remove again more than half of so this step is carried out for a finite number of steps. Then it says that you can reach magnitude which is less than the smaller than the original magnitudes. So it is given one quantity, and there is a smaller quantity, so more than half of that you remove from that, and go on removing more than half of whatever is left. So you can make the remaining remainder as whatever smaller than whatever you like. So that is the kind of what is called the principle of exhaustion. Okay. And as an application of this, one can prove that given any circle C and a real number, I have written this in terms of a modern language, given any circle C and a real number, so you should, they wrote it in terms of magnitudes, any real number epsilon greater than 0, there is a polygon inside C, say that the area of the circle minus the area of the polygon is less than the number epsilon. So sort of you can, in a sense, you can approximate the area of the circle by the polygons inscribed. That is, we will come to that also, a slightly more illustration of that. So for this, one needs a lemma, which is proposition number 1, book 12 of elements, that similar polygons inscribed in circles are to one another as the squares of their diameters. So this is, you can see that the two are related, and once you use these two, you can prove proposition 2, book of elements, book number 12 of elements. The areas of circles are in the ratio of their diameters. So this is one of the important theorems that was proved using the principle of exhaustion. And this is where it is not the definition of the area of the unit circle pi, but at least if you denote, if you assume that the area of the unit circle pi exists, okay, there is something called the area of the unit circle. And if you denote that quantity by pi, okay, then by this, you can say that the area of a circle of radius r is pi r square. So from there, this formula pi r square, which our school books have come up. But main thing is this theorem or an equivalent formulation of this is the ratio of the circumference to the diameter is a constant, which almost every book in mathematics at school level or even later on assumes to be the sort of an axiom and goes on. So at this stage, let me just ask what is the area of the unit circle? What is that? We said if we denote the area of unit circle by pi. This was only made precise much later in around 1872. But what Archimedes said is also important, and how they use the method of exhaustion is as follows. So I would like to exhibit that method of exhaustion by Euclid. So the idea is, given a circle of unit radius, you can inscribe inside a square. Okay. So actually the method is, you can do, for example, this square is the easiest one to do because you can draw two diameters and join. So the area of the square you can find out. And next, more than half of it, if you want to remove, you take the midpoints of these arcs and make it the octagon. And if you remove that octagon, that is the area of the octagon is more than half of the area of the square. So you'll get something. Okay. So let us see in the octagon if it is visible, the pentagon, and 7, 9, here is 8. So what is left is these areas of these arcs. So they are becoming smaller and smaller. So principal exhaustion says that the areas of these, some of these areas which are left out, not covered by the polygons, will become very, very small. And eventually saying that here is the method. Exhaustion includes implicitly, they are assuming something called the concept of limit. So if I, this is a software GeoGebra where we have tried to, so if we do it, okay. So you can see that the area of the polygons is increasing, and it is. So this is a very well-known software and applet now in GeoGebra, which can be used to in school level. So let me not go into that. So basically the principle of exhaustion can be very effectively used, and it was used by Archimedes to find out, to say that you can approximate the area of the unit circle. To make it very precise now, in our modern mathematics, if S is the area of the unit circle and Ln is the area of the inscribed to and gone, and Cn is the area of the circumscribed to and gone, then geometrically it is very clear that Ln is less than S. S is the quantity that we don't know, and it is less than or equal to Cn for n bigger than or equal to 2. And Archimedes showed that for I think n is equal to 3, this S is between these two numbers. And our school books took up S is approximately equal to 22/7. In fact, many of the books say that S is equal to 22/7. Okay, so that is the method of Archimedes. It does not define what is pi, but it gives a method of approximating. And where does the modern mathematics come in? The idea is that Cn minus Ln, that goes to 0. If we can show that as we increase the number of sides, In, the inscribed polygons, they are increasing. Cn's are monotonically decreasing. They are bounded sequences. So the completeness property of real numbers will say that they both converge. And as the difference can be made very, very small, one shows that the In and Ln both converge to the same value. And that is defined, that limit is defined as the area of the unit circle denoted by the Greek letter pi. This is all modern mathematics. This is not historically. Historically, they assumed, Archimedes assumed, Greek mathematicians assumed there should be something area, the region enclosed by the unit circle, and it was given the name as pi. So a method of Archimedes gave a very good way of computing approximation to it using the method of exhaustion. There is another principle called principle of exhaustion, also includes something called Archimedean property, which says that if you have a number between 0 and 1 and raised to power n, then that is equal to, limit is equal to 0. So that is another way of principle of, Archimedean property. So that is also hidden there, and it is assigned, attributed to Archimedes. Again, that is principle of exhaustion. So these are some of the consequences of the work of Euclid or Greek mathematicians. So let us just sum it up. What are the Greek mathematicians did not have the concept of real numbers. They knew only numbers through magnitudes. Okay. Very important. Real numbers were defined only later on in 1872, and I think around 1872 by Richard Dedekind and George Cantor independently, and they constructed real numbers using the field of rational numbers. Okay. Methods of Greek mathematicians were very rigorous. They knew what they are assuming and what they are proving. Okay. If they assume something, they wrote it clearly, they assumed that thing and as an axiom or whatever it is, and derived using them the results. They successfully avoided the concept of limits. Implicitly, they assumed it in the principle of exhaustion, but sort of geometrically they assumed, but abstract idea of limit was avoided. The area volumes were not defined. What is the area of a region that was not defined? What is the volume of something that was not defined? Only ways of computing them were given individually. Okay, so there were no general theorems, only individual computations were there. So their methods were not general, right? You can't call them as theorems, but germs of theorems were there in there. So this is the period 1 of the Greek antiquity. Right. So let us come to integration till the beginning of 18th century. There is not much known what happened after antiquity for about till many years, till about 1500 or 1600 years. But some of the people who made efforts to compute areas and volumes of various things and made success were Simon Stevin, John Kepler, Cavalieri, Pierre de Fama, Gregory St. Vincent, John Wallis, Christian Huygens, Pietro Mengoli, Isaac Newton and Leibniz. I have just picked out some of the names for which some examples I could dig out from the historical books. So I have mentioned them. Okay, right. Let me say one or two lines about some of them. For example, Calculator, the creator of modern astronomy, as far as integration is concerned, he calculated the volumes of wine casks. Okay, there is a famous, very well-known story about this. His calculation of wine casks. He was getting married, and wine was supplied by somebody in wine casks, the barrels, wooden barrels, for the party. And when the payment came for the supply of the wines, he wanted to ensure that the amount of wine supplied is really what the person is saying. So he calculated the volume of wine in each cask and then made the payments accordingly. Okay, so that is the story behind that. Kepler's second law, the focal radius joining planet to sun sweeps equal arcs in equal times, right? So that involves, in some sense, integration. Okay. Cavalier, next one, Cavalier, a student of Galileo, who gave a very famous principle called, now it is known as Cavalier's principle. If two solids have equal altitudes, and if the sections made by planes parallel to the bases and at equal distances from them are always in a given ratio, then the volumes of the solids are also in that ratio. Okay. So once again, the limiting thing is hidden, because physically you can make only sections, finite number of sections. So if the sections are finer and finer, you will get the corresponding formulas for the volumes. So here is he has devised a method of calculating the volume of a single solid in terms of cross sections, the section method of computing. For example, here is a stack of coins, and if I just bend the stack of coins, the volume does not change, right? The volume remains the same. So you can think of each coin as the section taken at a plane. So a plane at a particular height, a section is taken, so each section has the same volume. So the volume of this is same as equal to the volume of this by principle of Cavalier's principle. And if they are in a particular ratio, then the volumes will be in that ratio. Right? So that is the, in some sense, but the where is the limit hidden is that the thickness of these coins. If you make it smaller and smaller, then eventually that will lead to comparison of volume by slicing method. Essentially, that concept is here, which we teach as an application of definite integrals to our students. Right. Pierre de Fermat. I think by now everybody knows Fermat's name, Fermat's last theorem. He contributed not only in number theory, in algebra, and many other fields, and essentially he gave an argument for the proof of this formula. This notion of integral was not defined at that stage, not existing. Of course, he assumed the fact that limit, this is a mathematical fact which is used to compute this, that this is equal to this. A limit. So limit and concept is sort of assumed. Many things by mathematicians were assumed to be true, which they felt, oh, this should be true. And John Wallis gave a formula for integrating x to the power k when k is a fraction. So he, in some sense, extended the formula by Fermat. And Gregory Winston gave the area below the curve 1 over x. And if some of you may recall that integral of 1 over x the indefinite integral of 1 over x gives you the definition of logarithm. So calculus, fundamental theorem of calculus as an application. Now we can say we can define the logarithmic function very precisely by integrating 1 over x. And it was Gregory Vincent who had first anticipated this to be true. So these are some of the contributions of people in the 18th century. Finally, the things culminated in the works of Isaac Newton and Leibniz, who proposed independently their theory of calculus, differential and integral. And there is, I think in my lecture on overview of calculus, we had talked about the controversy between the two, who invented calculus. So let me not go much into it. There was a controversy which stayed for a long time. Who invented calculus, whether it was Newton or Leibniz. Both independently discovered it, did not discovered it, invented it, I should say. And Leibniz published it first, and then Isaac Newton saw it, and then that's how the controversy started. And there is a stark difference between the two, that he was a trained mathematician, Newton, while Leibniz was not a trained mathematician, he was a self-taught mathematician. So, so this is the tournament with the controversy between the two. I think if you're interested, go to Google and find out the controversy who invented calculus between Newton and Leibniz and read. It's interesting to read such things also. Okay. Right. So what was the contributions as far as we are concerned for both of them? Integration is to be found as the area between the graphs of two functions. Okay. This is modern language. Okay. This is only our language of trying to interpret the work of Leibniz and Newton, because the concept of graph was not very precise. The concept of function was not very precise when Leibniz came to the scene. Newton and Leibniz. Okay. So let us fix a point A and denote ZF equal to Fx, the area below the curve. Then Newton said, if you look at this way, then and you look at f of x plus delta x minus f of x, okay, then you can it is, which is approximately, so if you look at that strip x to x plus delta x, that strip is approximately equal to fx delta x. So sort of in some sense, integration is the reverse of differentiation. Okay, so that is the idea. So his idea was take small strips and add up. That should give you the area. And if you look up the areas and divide by the increment, that should give you the. So that is a fundamental theorem of calculus hidden here. Leibniz said his way of interpreting the integral was area as sum of rectangles. So he said you take points on the x1, x2, xn and form these rectangles, form the areas of the rectangles. Okay, and if you so if you call Zn as the area up to n, and so Zn minus 1 is f of at xn approximately delta xn. So as in the limit, if you divide by this, the dz by dx should be equal to f of x. So if Zn is z is the integral, then the derivative of the integral is equal to the integral. So that is Leibniz way of interpreting his theorem. Right. The contribution and Leibniz both we can summarize as follows: the recognition of inverse of relationship between integration and differentiation. So they both recognize that they are inverse of each other. And they also realize that the calculus, there are two different kind of calculus, namely one is probably what we call as differential calculus, and there is other called integral calculus. The two are mathematical, different mathematical subjects to be studied and analyzed. Systematic derivation of rules of these subjects and realizing the logical difficulties. They were trying to do systematical derivation of these formulas, and they realized there are difficulties in both of them. And the symbol of integration that we use nowadays is due to Leibniz in 1686. And the term integral was given by John Bernoulli, and was published in a book by his brother Jacob Bernoulli in 1690. So this is about integration, a bit of history. So people have struggled. So see, the aim from talking about history is how great mathematicians tackled these problems, which are conceptually difficult to understand, and how progress was made. See, now the notion of variable had been used by mathematicians over the centuries. The term function was first introduced by Leibniz. So Leibniz was the first one to introduce the concept of a function. Something is cause, something is the effect. He treated various geometric quantities such as a curve, tangents, normals, being functions of the curve. Okay, so tangent at a point on a curve, it is a function of the curve. Function was taken, this notion of function was taken over by Bernoulli, and gradually the function concept lost its geometric character, which was given by Leibniz, and John Bernoulli later defined it as follows. So his definition of a function is a variable. Now you see slowly how mathematics is emerging. A function is a function of a variable quantity is a quantity composed in some way or the other of this variable quantity and constants. So it's more or less to what we think of function nowadays, but that is not written that way. Okay, it is written as something that is composed in some way or the other. Okay, so that is a definition of given by Euler. Another great mathematician gave the following definition of a function. So what I am trying to do is how the notion of a function came into the picture, trying to understand the works of Leibniz and Newton, so that one could understand and say that there is something called differentiation and there is something called integration. Okay. So, for example, for Euler, if I say that Gx takes the value x plus 2 between 1 and 2 and x square between 2 and 3, Euler did not accept that this is a function. He said it should be composed of, expression should be composed of constants, right? But it is a single quantity, analytic expression. It should be something like this, a single expression, not broken kind of a thing. So he did not accept this as a definition of function. So this controversy between what is a function, okay, what should be called as a function, between Alembert in 1747, Euler 1748, and Bernoulli in 1753 was going on. And this also, this debate, what should be called as a function, started with the problem of vibrating string, which was being analyzed by mathematicians. So what is the vibrating string problem? So vibrating string problem is considered a string of length L put on, say, imagine it is put on the x-axis with both ends tied at 0 and L, right? And the string is plucked at some initial position. You pull up the string, so that is the initial position of the string, okay, and leave it so that it vibrates. So the motion of this, it was deduced that the motion of this is given by this partial differential equation del square y over del, because the position y is a function of two things. X, how far is the point from a fixed point, okay, say initial point, and at what time. So the position of the particle which is vibrating in the string is given by two things. It depends on two things. So it is a function of two variables in our modern language. It depends on two things: how far it is from a point, a fixed point, and what is the time point, at what point you are observing. Okay. So this is the motion is governed by this kind of equation, and and there are initial conditions at x is equal to 0 and x is equal to L. There is no displacement. Yxt is the displacement. So displacement is 0. This is called the boundary condition. And you can have the initial condition, the initial position of the string. So yx0 at time point t equal to 0, it is f of x. And if you are just leaving it, you are not giving any, with respect to time, you are not giving any impetus to the string to vibrate. It is vibrating of its own. So this is the initial condition for the vibrating string. So people ask for this vibrating string, what is the function y? Okay, what is the expression for y? So at this stage, Alembert said this y xt is given by the sum of difference of two functions, average phi of x plus at minus psi of x minus at by 2, where phi and psi, now here is the crux, are arbitrary functions of a single variable. Okay, phi and psi are, okay, here is the sum, here is the difference. So the second variables are intertwined in the first variable. With the boundary conditions, with the initial conditions given, that says, y of xt, okay, is given by half of f of x plus at minus f of x minus at. The solution should be given by this. Okay. Euler's objection, he also gave a solution to this vibrating string problem, as same as that of Alembert. However, Euler said that phi cannot be arbitrary function. It should be analytic function. Okay. So he says the solution of Alembert will work with different analytic functions appearing in 2. Okay. So that is Euler's thing. Bernoulli gave a totally different solution to this. He said the solution yxt should look like a superimposition of sine and cos functions, trigonometric functions. So it should look like some constant multiple of sine, and x, L is the length. Okay. So, and since it also satisfies boundary conditions, so f of x is equal to yx0. So f of x should look like this. Okay. Bernoulli believed that all functions can be expressed as 3. So here is the beginning of a series expansion for functions, namely a arbitrary function could be expressed as a superimposition of sine and cos functions. That is a claim made by Bernoulli. Okay. So here Euler came back to the scene. He said, look, in these 3, they are periodic functions. We are looking at superimposition of periodic functions. How arbitrary function could be sum of periodic functions. Okay. The crux lies that what does this symbol sum mean, right? That was not well understood at that time. In the equation 3, again, the right hand side is an analytic function. Okay. Sine and cos are formulas. While on the left hand side, he said these are all single formulas, but f of x need not be given by a single formula. That is the initial position. Okay. So there is a problem with this concept of a function. So this the controversy went on for about 7 to 8 years and raised important questions. So that is what is the important, the crux of this controversy was that does every function have a, is to be given by a single analytical expression or an equation? Does every function have a graph? Because when you plug that string, it is the graph of the function known, right? But does every function need to have a graph? Does every graph represent a function? So the relation between function, what is a function, what is its graph, and for given a graph, what is the function? Okay. So these things became to the surface no answers were available immediately. Okay. However, slowly it was believed that it is still believed that function should have a graph at that time. Okay, till Joseph Fourier came onto the scene. This concept, the interest in the concept of function. So there was a period when nothing was happening. So this was around 1500 something. So for about 300 years, nothing happened except when Fourier came on the scene, Joseph Fourier. So he was working on a similar problem, namely a function heat conduction problem. So I will not go into that, but he said a function is a relation in terms of variable, but it can take any values and need not be governed by a common law. So that is the interpretation Fourier gave. And he said, fine, that a function, so if I have a function between minus pi to pi, sorry, it should be representable as this. There is a lot of historical perspective, but eventually his claim was that a solution to the Fourier convergence problem, to the heat conduction problem, fx should be expressible as this. A function should be expressible. Once again, these cos and sine, they are trigonometric functions, and this sum we have written as 1 to infinity. For Fourier, this did not make sense at all. It was a superimposition of cos and sine. And now in modern times, we write it as an. He also believed that this an should be integral of fx cos mx, and bm is integral of minus pi to pi of fx into sine nx, right? So once again, mentioning that integral was only defined, was not defined precisely, it was only computed geometrically. Okay, in that sense, an and bn. So this is this came to be known as the Fourier convergence problem. For what functions you can write this, and for what functions this coefficients an and bn make sense. Okay, so this once again came to the question: what is the function? Which functions? For which functions integral can be defined? So that is how the concept of integral is getting tied up with the concept of a function. Because if you can define this an and bn for what kind of functions you can define, then you can analyze this problem for that kind of functions. So concept of integral got tied up with the problem of finding solutions for such kind of problems. So which functions have this problem? So as far as the function is concerned, the answer was given to what is a function was given by Dirichlet in 1822, who said function is just a cause and effect. So y equal to f of x. The modern terminology of a function, that is what is essentially the work of Dirichlet. Let me come to Cauchy now, because I think very important contributions were made by Cauchy as far as integral is concerned. And so let me say something about it. And I will also say something about the biographical sketch of Cauchy, because I think he was a remarkable mathematician and a remarkable person. Cauchy is credited with the foundation of modern age of rigor. So the rigor in analysis was instilled by Cauchy. The concept of limit, continuity, definition of integral all are due to him. The only slip, if we can say, is he understood uniform continuity as continuity. He was born in Paris. In 1789, he entered École Polytechnique in Paris in 1805, and he had great mathematicians as teachers, but they all advised mathematicians like Lagrange and Laplace. They were his teachers, and they advised that his health was not very good. So I advised that instead of taking engineering, École Polytechnique was supposed to be like an engineering college. And so he said, they advised him that you devote yourself to mathematics rather than engineering because your health is not that good. So, but he completed his training as a civil engineer in 1810, and he was given a commission in Napoleon's army as a military engineer. Okay, so he left Paris for Cherbourg as a first assignment. Despite his busy schedule, this is important. As an engineer, he found time to help local authorities conducting school examinations and doing his own research. Whatever spare time he had, he will do that. In 1811, he submitted his first work on the theory of polyhedra to Académie des Sciences, and second part was submitted in 1810. So this all research work was published and by the Academy of Sciences in France. In 1813, he returned to Paris and became a professor at École Polytechnique. Okay. And later he taught at the Faculté des Sciences, Collège de France. Okay. At that time, the King Charles was unseated. So Cauchy had shown that he will be loyal to Charles. So once he was defeated, he left his job and exiled himself to a place in Italy called Turin. So in Turin, he taught Latin and Italian for some years. Okay, he tutored the grandson of Charles X at Prague. Okay, and in 1838, he returned to Paris, where he served as a professor in several religious institutions. In 1848, after the revolution, the government did away with all the oaths people had taken. So he took over the chair of mathematical astronomy at Faculté des Sciences. Here is an important thing. He was a pioneer of rigor in mathematical analysis, created abstract history, and founded in the theory of groups, theory of elasticity in applied mathematics, ordinary partial differential equations, and complex function theory. Diverse fields he contributed, and he wrote about 500 papers in diverse branches of mathematics in the last 19 years of his life, till he passed away in 1857. A remarkable mathematician, very productive. So as far as integration is concerned, he defined the notion of integral as follows. He assumed let f a b be a continuous function. He has already defined the notion of continuity for a partition that is coming closer to what we do nowadays. To look at, say, value at the left hand point, f of xi minus 1, into the length of the interval. So that is the area of the rectangle with height as f of xi. And then take the limits of, I have called the CPF, they are the Cauchy sums, and take the limit of this as norm of p goes to 0. So norm of p is nothing but the maximum length of these subintervals. So if he showed that for a continuous function, this limit exists, and he called this as the integral of the function from the interval a to integral b. That was Cauchy's definition. For Cauchy, continuity meant uniform continuity. Okay. Of course, he assumed the notion of completeness of real numbers, which was only later on given by Richard Dedekind and in 1872. But he proposed and gave a proof of fundamental theorem of calculus, which is the crucial thing which connects mathematics, two parts of integral with the differential calculus. Okay. So it says, now in the modern language, it says if f is a function from a, b to r, and capital F is a function again from a, b to r, the small f is continuous, then these two are related by this formula. If and only if, that is important, f dash of x is equal to f of x. So you can interpret it as two parts. One part is if you recognize that small f is the derivative of capital F, then you can compute the integral, that is one part. And the second part says that if f is continuous, this is capital F is the derivative. So there are two parts of this fundamental theorem of calculus. which is the crux of integral calculus as far as computation is concerned and applications are concerned. Okay. So consequences of Cauchy, rigorous definition of area was given. Fundamental theorem of calculus as a inverse of integration was established. Fourier coefficients could be defined for Cauchy's integral, and elementary transcendental functions could be defined now. For example, the definition of log function could be defined using fundamental theorem of calculus, and other trigonometric functions also could be defined with a slight extension. So that is the work of Cauchy. Let me quickly say something about Riemann. Riemann's work, which is known to most of the people who have done undergraduate mathematics. It says basically if f is a function, continuous function, and p is a partition. So look at any point ai minus 1 in that interval. Okay, you can call it as a tag in that interval, and look at the sums SPF. We call it as Riemann sums. So he said the function f is integrable if this limit exists at norm of p goes to 0. Okay. A geometric way of defining the integral was given by Darboux, later on as in terms of upper sums and lower sums. Okay. Let me quickly, I don't have time to show that applet, but you can have a GeoGebra applet for upper sums and lower sums for functions. Okay. The important thing is, as far as the work of Riemann is concerned, the class of Riemann functions is quite large. Okay, Cauchy considered only continuous functions, but the class of Riemann integrable functions is quite large. There are functions which can have infinite number of discontinuities in every subinterval of AB, but still be integrable. This is a very important thing to say that the space of Riemann integrable functions is much larger than the class of continuous functions. Henkel gave example of a function, of a continuous function, which is not differentiable at infinite number of points. So that was a very surprise to many mathematicians, that you can construct a function which is in an interval which is continuous but not differentiable at an infinite set of points. Okay. But Carl Weierstrass in 1872 constructed a function continuous everywhere but differentiable nowhere, which was a real eye-opener for mathematicians at that age. And later on, Riemann proved this theorem that a bounded function f is Riemann integrable if and only if it's continuous almost everywhere. So the concept of almost everywhere essentially means that if you look at the set of discontinuities for the function f, you can cover them by a sequence of intervals of total length small. So that is called continuous almost everywhere. Okay. Here is an example of a function which is very simple and which we teach in our undergraduate mathematics, what is called the popcorn function. Look at a function f from 0, 1 to 0, 1. This function takes a value 1 at 0, 1 over q, when in the lowest terms, if x is equal to a rational number, p by q. So that look at in the lowest terms, so the 1 over q is the value, otherwise the value given is 0. So this is called popcorn function. Why it is also called Thomae's function. Why popcorn? Because the values look like popcorns. Okay, so one can show that this function is continuous at every irrational point and discontinuous at every rational point. So this is one example of a function which is discontinuous at an infinite number of points in every subinterval, but still one can show that it is a function which is Riemann integrable. So there is one example to illustrate that Riemann integrable functions is quite large. I'm skipping the details because each one, normally it is done in undergraduate mathematics. Or you can ask me later and I will send you the details. But as soon as Riemann extended the notion of integral from continuous functions to functions which are not necessarily continuous, there were many defects which became apparent. Namely, the foremost defect was the fundamental theorem of calculus that does not remain valid for Riemann integrable functions, right? If you recall, we said that capital F y minus capital Fx is equal to integral of ft dt a to b dt if f is small f is continuous. Okay, then only it is true. The second main drawback of Riemann integral is its behavior with respect to limits. Namely, if Fn converges, Fn is a sequence of Riemann integrable functions, so that Fn converges to Fx, then one cannot say that integral of Fn's will converge to integral F. In fact, Fn may be all integrable and converge to a non-integrable function. And you can also construct examples where Fn's are integrable converging to F, which is also integrable, but integrals don't converge. So in some sense, you are not able to interchange integral and the limit operations. One has to put strong conditions. We prove a theorem, namely, if Fn converges to F uniformly, then this thing is possible. So these are the drawbacks of Riemann integral. I will just spend one few minutes more to say beyond Riemann integration. And there is, if you denote by RAB the class of all Riemann integrable functions, one can define the notion of a metric on this space, namely dfg equal to integral of the area between the two curves, essentially you can think of. And here we are identifying functions which are equal almost everywhere. Okay. So for that, it satisfies the properties of a metric. So RA becomes a metric space. And whenever you construct a metric space, a natural question to ask is that metric space complete? So one asks whether you can say that under this metric, is it complete or not? Namely, does every Cauchy sequence in RAB under this metric converge? Okay. So that is actually not true, that every Cauchy sequence need not converge. One can construct examples. But then there is a theorem in metric spaces. We teach that every metric space can be completed. For example, the rational numbers are not complete, but you can complete it by putting it inside a bigger ordered field, and it sits inside a dense set. So here the question is, what is the completion of RAB, the space of Riemann integrable functions? Is the metric space which is not complete? What is the completion? And of course, we have said fundamental theorem of calculus does not hold for Riemann integrable functions. So Riemann was motivated by looking at the notion of integral because he was interested in analyzing the Fourier convergence problem for a bigger class of functions. Okay, so that's how we came to the notion of integral, and he extended the notion of integral. But in the process, many things were lost, and so mathematicians started working on this concept. So beyond 1902, beyond Riemann, efforts of mathematicians like Camille Jordan, Emil Borel, Bayer, culminated in the work of mathematician Henry Lebesgue in 1902, where he defined the notion of a new integral called Lebesgue integral. And the recipe for this integral is essentially that one should try to extend the notion of integral, because in the fundamental theorem of calculus, a function which is not continuous, only Riemann integrable. Riemann integrable functions are all bounded. So one can you extend the notion of integral so that the Riemann, so fundamental theorem of calculus remains true. So that was the basic idea, and it was realized. So this was the problem that occupied mathematicians for quite some time, called the extension problem. Define a class of functions from R to R such that it is a vector space like the class of Riemann integrable functions. RAB should be inside this class. It is something bigger than RAB. Keep in mind rationals and the reals. And this class of functions has the property that for a non-negative function, integral is bigger than or equal to 0. And integration, of course, has to be linear. So integral alpha f plus beta g should be alpha if plus beta phi g. And it has to be an extension for Riemann integrable functions. It should be equal to AB. For a Riemann integrable function, the new integral should be equal to the Lebesgue integral. And as much as possible, it should be free from the defects of Riemann integral. I think I don't have much time to go into the crux of this, but I will try to pinpoint one aspect where it differs. I will not be able to go into the sort of recipe for this extension, but the basic idea is, I think this will be a good idea to come to this slide. The difference between this Riemann integral and Lebesgue integral. So let me try to exhibit by a applet what is a crux. So here is a function. The graph of this function is this black one. In the right hand side, I am showing the Lebesgue integral. On the left hand side is the Riemann integral. So in the Riemann integral, what we do is we take a partition of the domain. Okay. So this blue are the partitions. At each point, we take what is called the rectangles. You can take either the inner rectangles. So there are only 3 inner rectangles, or you can take outer rectangles, upper sums and lower sums, and sum it up and find out what is the approximate area below the graph. In Lebesgue integral, instead of partitioning the domain, what one does is one partitions the range. So for the range of the function from 0 to 0.4, you take a partition, pull that partition back on the domain, and take rectangles on these partitions and add up the areas of these rectangles and try to take the limits, make the areas smaller and smaller. So that is the basic difference between the Riemann integral and the Lebesgue integral. In the Lebesgue integral, we take the partitions of the range and pull them back and define integrals and take the limits, while in Riemann integral, we take the partitions of the domain. Okay. So as you increase the number of partitions, you see that you get better and better. Okay. And you can easily see from even for 4, Lebesgue integral gives a better approximation for the integral. Okay. Right. So let me, so that is for what kind of functions you can do it, such things, pull back and so on. One has to define a machinery of Lebesgue integration. These are called measurable functions. For measurable functions, you can pull back the partitions and define the sums of rectangles. And also comes in between, when you pull back, you will not get an interval of a partition. You will get only some sets. So what is the size of a set? What is the length of a set? So you have to extend the notion of length to sets to subsets. So that is extension of the length function. That is the first step one does. And there is a whole machinery to be done for definition of Lebesgue integral. But as a consequence, this does, one proves that the Lebesgue integrable functions are in fact give you a completion of the Riemann integrable functions. One can prove that. There is a form of fundamental theorem of calculus which is available. A very satisfactory answer is available for fundamental theorem of calculus. I think I just want to show one last slide to indicate the difference between Riemann and Lebesgue integral in terms of Lebesgue himself when he introduced this. Oh, it's not playing. So I think, but I want to play this. It's not playing. So there is a link missing. So probably let me just see if we can pull the, I can show you that. So that that is only a,
So do you have the file with you?
yeah, I'm just taking that file only. Where is that file so that I can play the file directly from my,
Yeah.
I'm just trying to check that file. Maybe that file is not in that folder, it is somewhere else. Counting, it should be at C. Yeah, it's here. Okay.
So you need to share that file separately in a separate window. Yeah.
Yeah, I'll just do that. Let me stop it and share that file again.
So you need to click on this optimize audio and video, these options.
Yeah, I will do that also. Did I leave that? No, I am not. Okay. So I will stop and then share again. So just be with me for a minute.
It's already stopped, sir.
Yeah, share. So I'll be sharing. Is it visible now?
Yeah, yeah.
Where do I click for optimize?
No, while sharing, you had to.
Yeah, anyway, there is not much of audio. It's
okay.
Visual only, so no problem. So there are two ways of counting a bag of coins, as Lebesgue himself said when he presented this theory. So just look at the slides and the video. Why is not playing? Yeah. Yeah, so I think I will just stop here. And if any questions or remarks, I will be happy to react, to interact. You can unmute your mic and ask questions or say something if you want to say.
So there is one question in the chat.
Yeah.
Can you see it?
Let me just see. What is the, we'll start. I have seen the Weierstrass function. It is really looks scary. How could we get this complicated function without the use of computer? It's not difficult to, let me, who asked this question?
Sir,
Yeah. So let me just say something to make you feel easy that it is not that difficult an example to construct. You see, okay, if I have a whiteboard here, I will ask, okay, is there a whiteboard? No, I don't. Okay, let me just ask. So you use your mental board to go along with me.
yes, sir.
Okay. So look at the function fx is equal to mod x. What is the basic property of this function? It is a continuous function,
Yes, sir.
right? Say mod x between -1 to 1. Okay.
Yes, sir.
So is it differentiable?
No, sir. It is differentiable. It is not differentiable at the point x is equal. It is
Yeah,
only
x is equal to 0. So there is one point where it is not differentiable, right? So let me just do a small thing. Let us just reflect that function and think it like a triangle on the x-axis with the vertex at the point 0. So that is the graph of the function. Okay. Do you get it? Between -1 to 1, look at the graph. Okay, with at the point -1 it is 0. At the point at origin the value is 1, and it comes back to linearly at the point 1. So it is at kind of a hill. Okay, with maximum at the point 0. Is it okay? Hello.
yes, sir. I got it.
Yeah. So Atarana, be there with the responding yes and no, so that I know that I am talking to somebody.
Yes, sir.
Okay. So this is a function which is not differentiable at one point exactly. Can you make it not differentiable at 2 points remaining inside -1 to 1? I want to make it not differentiable at 2 points.
Then I can add another.
You can add another kind of a hill in between, right? But the point is, when I add up these, I don't want to go too far. So what I do is I reduce the height by half
Yes, sir.
and introduce two hills side by side of height 1. So two triangles of height 1, half, okay, in -1 to 0 and 0 to 1, triangles of half height. Is it okay? So that will be a function having not differentiable at 2 points.
Yes, sir.
Is it okay?
Yes, sir.
Yeah, if I add up the original function with this function, then do you agree that it will have 3 points of non-differentiability?
Sir, I didn't get it.
The original function, which was the bigger triangle,
Yes, sir.
that function is added to this function now. Sum of these two functions, will it have 3 points of non-differentiability?
Sir, the function, the real function which we got, it had 2 points where it was not differentiable.
Is there a whiteboard? I think there is a whiteboard somewhere.
Yeah, you can click on this share screen.
On the share screen, okay.
There is a whiteboard option.
Share screen, advanced sharing options.
No, in there only it should be there. I mean, one of the windows, there is a whiteboard option is there. Basic. In basic only.
I don't see share screen. I click, I get one participant can share at a time. Multiple participants can share, and advanced sharing. I don't see whiteboard. I would have loved to see whiteboard, but I can't see it. So it's where do otherwise I can't explain to him orally. Okay. See, the first function, let us call it as f1.
So F1 had a point where it was not differentiable. So
that was a point, 1 point not differentiable. Height was equal to 1, right?
Yes, sir.
So the height was 1. So so in the next, we modified this. We called the next function as f2, which has got height as half and 2 triangles sitting side by side in the same interval -1 to 1. Can you visualize that? Yes?
Yes, sir.
Yes or no?
Yes, sir.
Sir?
Yeah.
Yeah, the usual way you share your screen, you can click on the green button.
Okay, I click it.
What do you see?
Oh, okay. My whiteboard is there.
Yeah.
Okay. So let me now try to approximate. So here is, sorry, a very bad way of drawing, -1, and here is +1, and here is 0. Now let us look at what is the so here is the height is 1. So let me take this function going here and coming here. Is it okay? That was f1. F2 is go the height as half. Okay. So like this. Very bad drawing, but I can't help it because this is, I'm doing with a mouse. And then something like this. And then going from here, you go here, and then go. Call that as f2. Is that okay? This function as f2.
Yes, sir.
So what will be f1 plus f2? If I look at the function f1 plus f2, what it will be? It will have one, when you add it up, it will have differentiable, non-differentiability at this point, and at this point. Now go on increasing such things and adding. So go on adding this kind of smaller hills. The idea of making the height less is that if I go on doing it as a series, sigma fn, right? Then that function will have so many of non-differentiability points inside 0, 1 that they are everywhere. So every point will be a point of non-differentiability. So you are adding more and more non-differentiability points, and you want that series to converge uniformly, essentially. So that series should make sense, so that should converge uniformly. So that is essentially the idea of the stress function.
Small doubt, sir.
Yeah.
So when he is taking a point where it is not differentiable, so we are going in a like sequential manner.
Right.
So first only 1 point, then we have 2 points, then 3 points, and so on. We are approaching to a limit.
Yeah.
So my question was this, sir, that okay.
I'm not looking at the limit of fn. I'm picking up these fn's. f1 plus f2 plus fn, sigma. I want that series of functions to converge.
Yes, sir. So this small question that I had, so the set 0 to 1, the closed interval 0 to 1 is the set.
Your audio is not clear. The
Yeah.
0 to 1 is?
Uncountable. It is uncountable set, sir.
So what? Yes.
And now function f1, it has a countable number. It is countable number of points that it is not differentiable. Similarly,
No, that is a limit. That is the whole point. So look at the popcorn function. What is the popcorn function? The number of discontinuities is countably infinite, but they are everywhere on the interval. So try to understand the proof a bit more carefully. Okay, I think you will get it. The basic idea is go on introducing points of non-differentiability and reduce the height so that they remain summable. So that is the basic idea. Okay. Anybody else has a question to ask? Yes, anybody else has a doubt or a question or a remark? Because I did not prove any theorem, so probably everything is clear. If that is the case, probably you should, I think most of the things that I have talked about Riemann integral and the recipe for Lebesgue integral are part of chapter 1 of my book on measure theory. Historical things I have borrowed from a book by Felix Klein, is called History of Mathematics, 3 volumes. So I have most of the things I have borrowed from there. Anybody else? Can we get PDF? I think is it possible to Soumya to send make it available via a link?
Yeah, we can send to people who have registered maybe.
Yeah, registered participants will get a link for the PDF slide to be, right?
Or maybe whoever submits the feedback form, we can send them.
Yeah, those who have submitted feedback form will get the link for downloading the slides. That's a good idea.
Yeah.
So encourages you to fill up the feedback form. In between, if you want to ask something, please ask. Otherwise, I would like to say thank you to you all. About 25 people came. Type the name of the book we have just mentioned. The book is called An Introduction to Measure and Integration. An Introduction to Measure and Integration. Okay, that is available Indian edition by Narosa Publications. Or you can search the Google and you may be lucky to find a soft copy. Nowadays, everything is available as soft copy. Okay, thank you very much. Take care. If nobody has any more
questions,
questions,
sir. Yeah.
we close. Thank you, Soumya.